Greetings and welcome to this second video of the Introduction to R series. So in this video I will be going through the basic elements of the R language, which I break down into objects, functions, arguments, and operators. Now the R language, that is the R code that you will be writing, is a way of communicating with the R engine that executes your scripts. So what the R language is that it's an efficient and unambiguous language that tells R what to do. So for example, if you send the following code, mean x equals variable, and you run this, which on the Windows computers can be done by pressing Ctrl Enter. On Mac you can press Command Enter, and otherwise you can just press this button here, which runs the current line or whatever lines of code that you have selected. This code here communicates to R basically, hey, can you calculate the mean value of the variable object and return the value to me in the console? So when you run this code, R takes the variable object, calculates the mean value of the value stored in this object, and returns the mean value as output in the console. Now if you send the following instruction, var mean x equals variable, if you send this instruction to R, this is equivalent to saying to R, can you calculate the mean of the object variable and store this value in a new object that is called var mean? So if the instruction that you sent to R was sensible, for example, that the variable object contains only numbers and not, for example, words, then R will do as asked. So the elements in these examples above need some explaining. The R language can be broken down into the abstract elements of objects, functions, arguments, and operators. To put it simply, objects contain informations and functions take objects as arguments. The example code here, var mean, arrow mean x equals variable, consists of the objects var mean and variable, the function mean, which includes these parentheses here, and the argument within the mean function x equals variable. Now information, for example datasets, is stored in objects. Functions tell R what to do with objects, such as, for example, calculating the mean of some variable, to calculate the correlation between different variables and fit regression models to some sets of variables. Arguments tell functions what to do with objects, such as, for example, what the objects that the function is to be applied to are called, that is, where to find it in your R session, and, for example, how missing values are to be treated when the functions are executed. Now, operators, in a sense, are related to functions in the way that they tell R what to do with the objects or output from functions. So this arrow here, part of the code, is known as the assignment operators, and this tells R to store output as an object. So now we will go on to providing more detailed explanations of these basic elements of objects, functions, arguments, and operators. So objects are containers for information that can be, you can make them, you can change them, or you can call them when working in R. So most people with experience from other software such as SPSS will be most accustomed to working with data frames. which are variables that are represented by columns and individuals represented in rows. In an R session, a data frame will usually be stored in the environment as an object. So using R becomes easier once you realize, or once you start to think about data in a somewhat different way from what you might be accustomed to from other software such as SPSS. That is, variables are not necessarily stored or organized in data frames. Rather, variables can be stored separately as vectors. In RStudio, stored objects in an R session can be seen in the environment window. And as you can see here in the environment window, I've stored already the variable object, which I made prior to recording this video. And you have this var mean object, which I made using this code. So this top here, this variable object includes 100 values. And you can see a minor selection of those here, starting with the first. And this var mean object is also a vector, and however it contains only a single value, which is the mean of the variable object, which is what I asked R to calculate here using this line of code. So this, you can see the objects of your R session, you can see in the environment window. So as I stated previously, what type an object is determines what you can do with it. So, for example, you cannot calculate the mean of a variable consisting of words. And for that reason, you cannot use an object containing words with the mean function. Now we can check what class an object is using the class function and feed it an object such as the variable object, which I got stored here in my environment. And you can see that it returns that the class is numeric. Now, simply typing out the name of the object without feeding it to the function simply prints the object into the console. So if I simply write variable here and execute it as code, we see that the contents of the variable is printed to the console, or printed in the console. So it's important to note that R is case sensitive, so that it's important that I write out the name of the object exactly as it is stored in the environment window here. If I write variable with a large V, an uppercase V, and try to run this, I will get an error because the object name variable with a V, or with an uppercase V and a lowercase v, are considered different names in R. It doesn't refer to the same object. So moving on to functions. As I previously stated, functions do things to objects in accordance with certain specifications. So these specifications are referred to as arguments. So functions consist of a name followed by parentheses. So the mean function consists of the name mean and followed by parentheses, which sets the scope of the function. It is within these parentheses that the arguments to the functions are specified. So often, but not always, the first argument tells R which object the function is to be applied to, and the remaining arguments contain additional instructions regarding how the object is to be treated by the functions. So one important exception to this general rule is found in the LM function, which fits linear models to data, for example, regression analysis. And in the LM function, the first argument is the specification of the model, and the data that the model is to be fitted to is the second argument. So optional arguments are often set to sensible defaults and need not be specified. Optional arguments are arguments that you do not necessarily have to change or to write out when you are using the argument, but there are situations where you might want to change the default to some other value. So to take the mean function as an example yet again, the arguments of the mean functions can be seen in the help file of the mean function, and help files you can access using this question mark and followed up by the name of the function. We can see here that the help file appears down in the plot window. We can blow this up a bit to inspect it. So the help file then contains a fair amount of information regarding the general use of the function, and learning how to read these help files, as I already stated, is one of the most important skills that you need to learn in R in order for using R to be a more pleasurable experience. So what we can see here in the help file is that first of all we get a general description of the function. That is, this function is used to calculate the arithmetic mean of a variable. The usage of this function is mean parentheses x dot dot dot, where the dot 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 refers to the additional arguments. Now x here then refers to an R object, for example variable. I fed, as you can see here, the first argument x equals variable. I assigned the variable as the object to which the mean function was to be applied. So, and you also have some additional optional arguments, which are in this case set to sensible values so that I don't have to change the defaults. However, if my variable object were to consist of missing values, I'm just imputing a missing value here for the purposes of demonstration, not worry too much about the code yet. If I now were to execute this code again, that is to ask R to calculate the mean of the variable object, it returns NA, which is the R code for missing values. That is, when my object contains missing values, I have to manually specify to R to calculate the mean of the variable by removing the missing values from the object. So what I do this by specifying this additional argument, which you can see here as part of the help file. I ask the function to calculate the mean of the variable object and to remove the missing values from the variable object before calculating the mean. So na.rm stands then for missing values remove. And this is set to false by default, as you can see here. That is, the mean function in R requires that you do something with missing values before you apply it, or else it will simply return a missing value itself. So, specifying arguments within functions. Up to this point, we have been writing the arguments out in full. So the complete way of asking for the mean function then is to calculate the mean for a vector, where you say mean equals x equals variable, which is then the first argument of the function. However, the x equals here is actually unnecessary because I'm inputting the arguments in the order that is listed in the help file for the function. Now, if we want to tell R to remove the missing values from the variable before calculating the mean, that is to change the value of the NARM argument from false to true. If I were to do this, remove the NARM part of this argument like this, and run the code, then R would have a problem. That is, it would think that this true value here was then supplied to the trim argument, since the second argument of the mean functions is trim, not NARM. So that if I'm not adding information in the order that is listed in the help file here, I will have to further specify which argument an object, or which argument an object belongs to. So now I'm specifying NARM equals true. That is to say that I'm skipping the trim argument, so to speak. I'm not changing the defaults. And since I'm not providing any information to the trim argument, I have to specify that the next argument I'm providing instructions to is the NARM argument. So that is the basic functionality of a function. That is, it is the name of the function followed by parentheses, and within these parentheses you specify the arguments of the functions, which are, for example, the data that the function is to be applied to, and additional instructions to the function with respect to how it should handle different occurrences, such as in the case of the mean, how it should handle missing values. Now, moving on to operators. Operators function somewhat similarly to functions in the sense that operators, some of them actually take the form of functions. So there are several types of operators. The most commonly used ones are the assignment operators, which are the arrows that we saw above, and also the equals sign actually. You also have the arithmetic operators, which are what you are used to as the plus, minus, multiply, divide by, raise to the power of, square root of, log of, exponent of, etc. And you have the logical operators. There are many different logical operators. Some of the most common ones are, for example, the is equal to operator, the is not equal to operator, but you also have things such as the less than or equal to operator, the greater than or equal to operator, etc. Now we will be going through these different types of operators in turn. So for the assignment operators, these are used to store, meaning to assign values to object. So common practice is to use this arrow assignment operator outside of functions, and to use this equals assignment operator inside a function. So, for example, the code mean of x, mean x equals variable, or as we just learned, I don't have to specify this x here because the first argument of the mean functions is the data that is to be applied to, but also what we learned, since I've imputed the missing value as the first, I have to specify NARM equals true. So what this does then with this assignment operator is that I tell R to take whatever comes out of this function here and store it in a new object called mean of x. So this assignment operator is what makes R store the output of this function into this object. So if I run this, the variable or the output of this function is stored in a new object called mean of x, which can be found in your environment. So that means that I can call this object at a later point whenever I have need for it. And by calling an object, it shows up in the console window, the contents. Now the equals sign, the equal signs, which we see here inside of this argument here, or inside of this function here, is then used to assign the object variable, in this case, to the what will be a function internal object called x. So a bit advanced, so it's not really anything that you should worry about at this point, is that functions have internal environments when they carry out what they're supposed to do. So all functions then have their own internal environments that are separate from your global environment. However, speaking of function internal and functional external environments is a bit complicated, and it's not something that you should bother with at this point. The main takeaway the main thing that you should take away from this is that while the arrow operator and the equals operator functions somewhat similarly, the main convention is to use the arrow operator outside of arguments and the equals operator inside of arguments. And there are reasons for this, but I won't get into it. Just follow this convention and you won't get into problems. So moving on to the arithmetic operators. The arithmetic operators basically allow you to use R as a calculator, and they instruct R to perform arithmetic operations on numeric vectors and also logical, but we will get back to this later. So for example, it's simply writing out 3 plus 2 and running that as code prints out the value 5 in the console. So because 3 plus 2 equals 5, and the 3 squared would then be 9, that is 3 times 3 is 9, etc. And the square root of 9 is 3. And where the square root is an example of an operator taking the form of a function. That is, you have the function name, you have the parentheses, and you have supplied the object 9 as the first argument to the square root function. So we can go on for using many different of these operators. So we can, for example, take the natural logarithm of 9, you can take the exponent of 9, etc. So there are a lot of different arithmetic operators that you can make use of. Furthermore, you can actually raise an object to the power of another object, or rather combine two objects arithmetically, considering or presupposing that the objects are numeric. So for the sake of it, let's just make 2 vectors here. The first vector is the sequence of values from 10 or 1 to 10, and the second vector is the sequence of values from 10 to 1. So inspecting these, my vec 1 and my vec 2, see that these are 2 sequences of values, where the 1 on the myvec 1 corresponds to the value 10 on myvec 2, the value 2 on myvec 1 corresponds to the value 9 on myvec 2, etc. So we can do arithmetic operations where we combine these 2 vectors. So if I do my vec 1 plus my vec 2, for example, each individual element in these 2 vectors are added to each other. So 1 plus 10 is 11, 2 plus 9 is 11, 3 plus 8 is 11, etc. So I can also multiply these by each other, where 1 times 10 is 10, where 2 times 9 is 18, 3 times 8 is 24, etc. And this goes also for raising to the power of, dividing by, etc. So in that sense, it is exceptionally simple to transform variables in R. That is, you can apply any numeric transformation without any issues. So, for example, squaring my back 1 would amount to a squared transformation of the variable my back 1, and the square root of my back 1 is then the square root transformation of my back 1. You can save this like my square root back 1, and voila, you have your square root transformed variable. So, for example, one popular transformation of variables is the standardization. That is, you make it so that a variable has a mean of 0 and the standard deviation 1. So this can be done quite simply for the myBack1 object, doing like this. You have myBack1 minus the mean of myBack1 divided by the standard deviation of myBack1, which then produces a vector of Z values. Now if I store this as my Z values and I check the mean of my Z values and the standard deviation of my Z values, you see that this here then is a standardized variable with a mean of 0 and a standard deviation of 1. So this code here is essentially equivalent to telling R subtract the mean of the values in the myBack1 variable object from all of the values in the myBack1 object, and then divide all of these values by the standard deviation of the values in the myBack1 object, which then produces a vector of Z transformed scores. So the first line of code tells R to perform the transformations and then to print the values in the console. And the second code that I wrote here then tells R to perform the transformation and store the output in an object that we named myZvalues. So moving on to the logical operators, these are useful for doing logical checks and are particularly useful when programming in R, but also exceptionally useful when you are subsetting your data. So these operators are then useful for doing logical checks, and they return Boolean values, which are values that take on either true or false or 1 or 0. This equals operator here can be called the is equal to operator, that it checks for whether two values are the same. The exclamation point equals operator can be called the is not equal to operator, which checks for whether two values are not the same, returning true if they are not. Here you have the greater than operator, the lesser than operator, the lesser than equal to operator, and the greater than or equal to operator, and you also have the AND operator and the OR operator. So these operators here can be applied to variables. So taking the myVec1 as an example, if you use the code myVec1, remember that this is a sequence of values running from 1 through 10. If we say myVec1 is less than 5, this returns the value true for all values in myVec1 that are less than 5. So 1 is less than 5, which returns true. 2 is less than 5, which returns true. 3 is less than 5, true. 4 is less than 5, true. 5 is not less than 5, therefore it's false, and it's false for all values above 5. So this code here then produced a logical vector, so I can, as always, assign this to my logic vector. And whenever then I call this object my logic vector, it's then got these Boolean values stored. So we can go on with this for many different logical checks here. Printing the myVec1 again. We can find all the values in myVec1 that are less than 5. We can find all of the values in myVec1 which are greater than 5. And you see that this reverses this, where all the values that were true in the previous are now false, and also the 5 remain false because now we're asking for the values above 5. If you want to include a value 5, we can say myVec1 greater than or equal to 5. So this is then the same, produces the same vector, except that this time you return a value true for the value 5 as well. We can check myVec1 is equal to 5, which returns true only for the value 5. And we can do myVec1 is not equal to 5, which returns false only for the value 5 and true for all of the other values. So as I said, these logical operators are particularly useful when programming in R, but for ordinary use they are also very useful for subsetting, which means to divide or split up data. So for example, take a data frame stored in an object named dataset, where you want to make or to split the dataset into 2 separate data frames, one for men and one for women. Now imagine that the dataset contains a character variable named gender with the values male and female. We can make a new data frame containing only data from males and one only containing data from females using these logical vectors. So first we can actually make a fictitious data set like this. So we have data set, it is a data frame consisting of C, R norm 180, 15, 100 values, the 180 and let's say 15, norm 100, 160, 10, repeat, male, 100, C, rep, female, 100, and we can call this first variable here height, and we can call the second variable here gender, So this then produces a data set. Let's see, head data set, where you have two variables, one of height and one of gender, so that you have registered the height of males and the height of females, 100 males and 100 females, so 200 to be specific. Now, if we do tail of this data set, you see that it also contains values for females. Now, if I want to make a data set that only contains the male portion of the data set, I can do it like this. I can make a new object called data men, and I go into the data set object and I subset it where I want all the columns, all of the rows, for which gender is equal to male. And I want all of the columns. And I can do this similarly for females. I want to make a new object called data female, and I assign to this all of the rows for which the gender variable has the value female. Oops, what happened here? I didn't finish this. Let's see. So now I've made one object, data men, which contains all of the observations for those who had the value male on the gender variable, or the gender vector within the dataset object, and another dataset that only contains the values from the original dataset for which the value on the gender vector was equal to female. You can see here, inspecting these rows, that the original dataset here contained 200 observations, while this data men extracted only 100 of these from the original dataset, that is all the males. And you have the second dataset here, data female, which have extracted all of the values from the dataset that for which the gender variable was equal to female. So the logical operators are extremely useful for subsetting data. So the above here then presents an example of where logical operators are particularly useful. It introduces some advanced use of logical operators when it comes to subsetting data, and it is at this point not expected that this subsetting operation would make sense to you. However, it does provide a preview of the usefulness of using these logical operators in case you were wondering when you would ever need to use them.